Now that we have a lot of limit properties, and we have some ways to calculate specific limits, like the limits of polynomials, the limits of rational functions, let's see how we can apply these things, right? In this lecture, we're going to look at the limits of a variety of functions that are unusual in some way, right? Where we have to go beyond just straight substitution. Now, okay, this first one is straight substitution, right? Because I just want us to remember what our starting point is, right? The limit of a polynomial as x approaches a number is just the polynomial evaluated at that number. So this will be 3 times negative 1 to the fourth minus 2 times negative 1 squared plus 4 times negative 1 minus 2. Let's see, straighten out all these exponents. That's 3 minus 2 minus 4 minus 2, 2, 4, 8, 3 minus 8, that's minus 5. That's kind of the base method that we're going to use as our starting point when evaluating limits. Just put the number in, right? Just put the number in and kind of see what happens. All right, so let's take a look at this one. Right, I'm going to try that same method here, right? If I just substitute 5 into the expression, I get 5 minus 5 over 5 squared minus 25. All right, 5 minus 5 is 0. 25 minus 25 is 0. And that's not defined. Right, that's not defined. So, before we just throw up our hands and say, okay, well, the limit doesn't exist, you always have to stop and think, can I play with this a little? Anytime I see 0 over 0, I'm thinking, okay, maybe I can do something that's going to make the factor in the numerator that's making it 0 and the factor in the denominator that's making it 0 go away. All right, so here's what I'm going to do here. Right, I'm going to factor that numerator and see what happens. This becomes the limit x minus 5 over x plus 5 times x minus 5. You see, that's what I was hoping. Still, x approaches 5. These x minus 5s, they cancel. All that's left now is the limit x approaches 5 of 1 over x plus 5. And now I'm going to do it. I'm going to go back to the beginning. I'm just going to put 5 in. See what happens. If I put 5 in here, this becomes 1 over 5 plus 5. That's 1/10. And that's it. There's my answer. All right, so if you think, if we try graphing this function, right, if we try graphing this thing, and I'm specifically looking at this function here to think about what I'm going to graph. It has a vertical asymptote at the x-axis, and it has a horizontal asymptote at x equals -5. And the function itself, it's kind of this very basic hyperbola kind of shape, except you got to remember this factor that we canceled out. The function is undefined there. So it's undefined when x minus 5 equals 0 or when x equals 5. So how does that affect the graph? Well, if I go over 1, 2, 3, 4, 5, this means that there's a hole there. You remember, holes really don't affect the limit. As I kind of get closer and closer to that x coordinate, the y coordinates are centering in on a number, whatever this y value right here is, and it turns out that y value is 1/10. That's what we've shown here, right? That's what we've shown. Okay, so how about this one? A similar problem, that's the limit as x approaches 4. If you put 4 into here, you get the square root of 4 minus 2 over 4 minus 4, and that's 0 over 0, the same kind of problem scenario that we had before. Okay, so I'm going to kind of apply the same strategy and hope that I can simplify this away. And here's how I'm going to do it. This is going to maybe seem a little weird to you, because you don't usually think about doing this. I'm going to rationalize the numerator. Yeah, I know, usually we're doing that with the denominator, right? Here I'm going to do it with the numerator. So I'm going to multiply the top and bottom by the square root of x plus 2. All right, so the top, this becomes the square root of x squared minus 4. And the denominator is x minus 4 times the square root of x plus 2. And don't forget the limit. This is still the limit as x approaches 4. That's a common mistake I see students make. They get so focused on the simplification and the manipulation that they're doing that they forget to just keep writing that limit part over on each line. And where that causes them trouble is this will take them 4 or 5 steps, and by the time they get to the last line, they've completely forgotten that a limit is what they're trying to find, right? Because they stopped writing it so long ago. So be sure to keep writing that. It's really almost just as a reminder to you that that is what we're doing. You do have to take the limit on the final step. Okay, so this is the limit x approaches 4 of x minus 4 over x minus 4 times the square root of x plus 2. And look, it happened again. The x minus 4's cancel. All that's left is the limit, right? We're going to keep writing this every time. 1 over the square root of x plus 2. Now I can just put 4 in, right? I'm just going to put 4 in. This is 1 over the square root of 4 plus 2, which is 1/4. And that's it. There's my answer, right? We're done. All right, so let me give you one. Take a look at this. See if you go ahead and pause the presentation. See if you can't figure this one out. Then start it back up, and we'll do it together. Okay, so if you just drop -3 in there, you get the same problem we've been seeing over and over. You get 0 over 0. Okay, so I know that x squared minus 5, it's that square root, the numerator's a little busy, but look, I'm just going to do what we've been doing. I'm going to do what we did before. I'm going to try to rationalize away this numerator. So I'm going to multiply the top and bottom by 2 plus the square root of x squared minus 5. Okay, so in the numerator, right, this is still the limit x approaches -3. The numerator is 4 minus the square root of x squared minus 5 squared. And the denominator is just kind of a mess. It's x plus 3 times that thing. 2 plus the square root x squared minus 5. All right, so look at what happening up on top. The top becomes the limit x approaches -3, 4 minus the quantity x squared minus 5 over this kind of messy denominator, 2 plus the square root. Okay, so let's see, I'm going to still limit, right? Limit x approaches -3. Let's distribute that minus. This becomes minus x squared plus 9, plus 5, and 4 plus 5 is 9. This is all, that denominator is not going to go anywhere for a little bit. At least one more line. Square root x squared minus 5. Okay, that numerator, it factors. This is the limit x approaches -3 of negative x plus 3 times positive x plus 3. And this is the good things happen step. Now the numerator is the same. And now the numerator, the denominator is the same. Now the denominator is going to change. These x plus 3's, they cancel. right? And all I'm left with is the limit x approaches -3, negative x plus 3 over 2 plus that square root. Now I'm going to try again. Now I'm going to put -3 in there and see what happens. This is now -3 plus 3 over 2 plus the square root of -3 squared minus 5. Okay, the numerator, that turns into 3 plus 3, that's 6, over 2 plus, and what's going on in here? This is 9 minus 5, so that's the square root of 4, which is just 2. So this is 6 over 4, which is 3/2. That's it. Now we're done, right? That's my limit. Okay. So how about this? This is a new tool, right? This is a new tool, and I know it's a little wordy, a little weird. This thing is called the squeeze theorem, sometimes called the sandwich theorem. Right? What it says, and I'll give you a sec. Go ahead and read that through, right? And then we'll talk about it. So here's what it's saying. I have these three functions, f, g, and h. And I know they're kind of stacked, right? F is on top, g is in the middle, and h is on the bottom. And they're always that way. They're never going to cross each other. Okay. And I have this one special piece here. Remember, f is the top function, and h is the bottom function. We've got this point here, x equals a. And what this is saying is that at a, the limit of f and the limit of h are the same. Okay, so if I were to try to draw these, I have f of x here, and I have to draw h of x with two criteria. First, it has to be always below f, and second, the two of them have to come together at a so that they have the same limit. So h is going to look like this. Okay, now what about g? G, remember, is sandwiched between the two of them. So it's doing, I don't know, it could be doing all sorts of bizarre craziness in here, but when it gets to this point, it has to meet up and slide between the other two, right? And that's what this last part is saying. The limit of g of x at a is also L because it's squeezed down in between the other two. Okay, this is a slightly unusual theorem. It's a great theorem. We're going to be able to do some really good things with it. But it's also not one that you're going to be bringing out of your toolbox every day. Okay, because finding these two very specific functions that exactly bracket the function you're interested in and where they both come to that same point, it's not always going to be easy. Okay, but I do want to do an example, right, so you can see how this is used. So I'm looking at the limit of the sine of theta. So you brought trig functions into the party now, right? How are we going to handle trig functions? Well, I'm going to use a rule here. Okay, I'm going to use a rule. Negative absolute value of theta is less than or equal to sine theta is less than or equal to the absolute value of theta. Okay, this is true when theta is small. And I'm okay with it being small because I really only care what the functions are doing in a neighborhood of 0. Right, so let's look at what this is telling us now. Right, let's try a quick sketch. The absolute value of theta looks like this. Right, work with me. Pretend these lines are straight. The absolute value of negative theta looks like this. the negative absolute value of theta looks like that. And I know that my sine function is bouncing up and down, doing the things that sine functions do, but it has to stay between these two, right? So because the limit as x approaches 0 of the absolute value of theta equals the limit as x approaches 0 of negative absolute value of theta, and those are both equal to 0. And because our sine function is squeezed or sandwiched between those two, then the limit as x approaches 0 of sine theta must also be 0, right? And that's what we were trying to show. Okay, like I said, great tool. We're going to use it to great effect a couple times throughout the class. But it's not one you're going to use a lot. When you're doing homework problems, it's probably not the first place you're going to want to go when you're looking for a technique to use. Okay, so where are we going next? There are some functions that are a little interesting. Look, for example, at f of x equals the square root of x. Okay, that looks like this. Okay, what about the limit of the square root of x as x approaches 0? What is that? Well, my answer has to be it doesn't exist, right? It doesn't exist. I'd like it to be 0, right? That's what the square root of 0 is. I'd like this to be 0, but it's not, and here's why. It's a real technical thing. If you pick an interval around 0, right, the L0, this is your epsilon, this is your epsilon. I have to be able to find an interval around x equals 0 where every x value in that interval gets mapped into your epsilon interval, and I can't do it, right? Because the function isn't defined over here on the left-hand side, right? So I can't do it. The limit, my conclusion has to be that the limit does not exist, and that's a little bit of a problem. It's a little non-intuitive. The square root function on its domain is well behaved. It doesn't have gaps, it doesn't have holes, it doesn't have asymptotes, it doesn't do weird bouncy things. I'd really like for that interval at the left-hand endpoint of the domain, where the function is perfectly well defined, to somehow exist. Okay, that's what we're going to talk about in the next section. We're going to talk about what can we do about otherwise well-behaved functions that have unlimited domain.